Hi everyone, I'm Wei Hu. I'm going to talk about our work on the case for offload shaping. So I guess everyone in this room are familiar with the concept of offloading. That is to offload the expensive computation from the mobile device to a server on the cloud or on the cloud device. And there are also a lot of work discussing how to partition this computation between the mobile device and the server. But that's not what this talk is going to be about. This talk is about offload shaping. In this work, we propose to put additional computation on the mobile device to shape the workload of the offloaded computation. That is, to use the additional computation to discard some data early on the mobile device to avoid expensive computation altogether. So this additional computation on the mobile device is not a part of the original computational pipeline. It's extra work, but it's so cheap that its benefits outweigh its costs. There are several potential benefits. First of all, as we're discarding some data early on the mobile device without sending it over the network, we save Wi-Fi bandwidth. Also, as the mobile device is transmitting less data, we may save mobile energy too. Also, the server is doing less work. And all these benefits come at the cost of little accuracy loss. So this is what we call offload shaping. So in this work, we first investigated several examples of offload shaping and show that we get significant resource savings in all three examples. The first example is about discarding blurry frames. The second example is about similar frames. And while we imagine discarding blurry frames and similar frames can be beneficial to a wide variety of applications, some applications may have its own need for offload shaping. So in the third example, we investigate context-sensitive cases. We use color filters as a specific particular example, and we also discuss how we leverage hardware accelerators. Then we propose an offload shaping API for applications to do this easily. So for the interest of time, I'm not going to cover the hardware accelerator part. You are very welcome to read our paper if you are interested. Now let's start with the first example, discarding blurry frames. So by discarding blurry frames, we want to save bandwidth, energy, and server workload while only sacrificing a little bit accuracy. Before we start, one question pops up: are these goals plausible? Like, is it even possible to achieve all these goals at the same time? So let's look at a perfect blur detector to see if these goals are possible to be achieved at the same time. We consider the perfect blur detector to be one that's using human knowledge. So we run a case study. We take 259 frames from the video and ask two people to label each frame as sharp or blurry. As you can see here, we get about 150 sharp frames and about 100 blurry frames. When we record the video, we make sure that a code can exists in every frame. So then we feed all these frames to an object detection called Moped. We ask Moped to detect the cocaine in it. As you can see here, in almost every frame labeled as sharp by people, Moped detects the cocaine in it. And in almost every frame labeled as blurry by human being, Moped fails to detect the cocaine in it, although we know as ground truth there is a cocaine in it. So it seems that although we are sending these blurry frames all the way to the server, we're not able to extract anything meaningful out of it. So we built a perfect blur detector which uses human knowledge to detect blurry frames in no time. And we discard those blurry frames and just assume nothing is going to be detected there. The only frames we're going to get wrong is the tiny blue parts down here. As we can see, it's pretty small, so the accuracy loss is actually only 3%. Meanwhile, we're transmitting 33% fewer bytes. The glass is consuming 32% less energy, and the server CPU usage goes down by 19%. So it seems like the perfect blur detector is giving us all the benefits we want with only little loss of accuracy. Then how do we build a real blur detector to get similar performance? The first idea is to look at the image itself. Blur detection is well studied in image processing, and there are a couple of ways to do it. We choose a method called Sobel operator as it's relatively lightweight. The main idea of Sobel operator is to detect edges in the picture. The pink squares here are an overlay showing the edges detected. If you look closer, you'll see like white lines in the pink area. They're the edges detected in that area. As this frame is relatively sharp, the white lines look pretty clear. For a similar picture that is blurry, it's very hard to see the edges. So using this knowledge, we can detect whether a frame is blurry or not. Another idea to detect blurry frames is to use sensor data. Sensor data is the source of the blurriness in frames captured on mobile devices. Then which sensor should we use? One common idea is to use acceleration sensors. Acceleration sensors are usually used for motion detection. However, we found that we cannot use acceleration directly in this task, as blurriness is more related to velocity instead of acceleration. For example, in a typical movement like shaking my head, I'm going to get a couple of blurry frames on my Google Glass. But actually, when I shake my head to the rightmost position, I get one sharp frame because my velocity is 0 at that moment. But my acceleration is actually at its maximum value. So we need to integrate acceleration to get velocity to properly detect blurriness. However, the integration process is well known for larger cumulative error. So to keep things simple, we choose gyroscope instead. Gyroscopes are common on smartphones, and Google Glass also has one. Gyroscopes give us angular velocity, so no integration is needed. And angular motion is actually the main source of motion blur in the context of wearable devices. For example, it's very common for you to move your head when you are wearing a Google Glass. And when you do that, everything will move really fast in your view. That's the source of motion blur in a lot of cases. So in this work, we built a blur detector using Sobel operator and another one using gyroscope. Let's see how they perform. So this table is the blur detector using Sobel operator. Numbers in green means that things are improving, and numbers in red mean things are not as good. As we can see, now we're transmitting 27% fewer bytes, end-to-end latency goes down by 7%, and we're consuming 9% less energy for each frame on Google Glass. The server CPU usage also goes down by 16%, and the cost is only 5% accuracy loss. So this may not look as good as the perfect blur detector, but it's also giving us all the benefits we want with only a little loss of accuracy. And what about the blur detector using gyroscope? We see very similar benefits, like 27% fewer bytes transferred, 18% shorter latency, 20% less energy, and 16% less server CPU usage. And the accuracy loss is only 8%. So these two tables show that discarding blurry frames gives us the resource savings we want, while the accuracy loss is pretty small. Now let's look at the second example, similar frames. So while we design our systems to take care of fast-changing scenes, there are times the wearer of the Google Glass may just want to sit there and enjoy a good view. So then the content will change very slowly in the video, and we are going to get a lot of similar frames. In this case, it's quite safe to assume that whatever appears in in one frame will stay there for a couple of more frames. So if we can detect some frames are similar, we can just discard them early on the mobile device and just assume whatever is detected in the last frame is still there. So one question pops up: why don't we just lower the frame rate? If instead of 30 frames per second, we capture 1 frame per second, then we are going to automatically get rid of a lot of similar frames. The answer is responsiveness. Although we want to save resource, we don't want to give up the responsiveness of our systems. For example, if a new object shows up in the middle of a second, we want our system to be able to react to it at once. We don't want to wait until the end of this second to receive the first frame containing this new information. So to preserve responsiveness, we need a proper way to detect whether 2 frames are similar or not, and only discard the similar ones. The way to do it is we use a technique called perceptual hashing. Perceptual hashing basically calculates a hash value for each picture. And this hash value is quite different from the hash we usually talk about. The magic thing about this hash value is that the distance between two hash values actually indicate the perceived difference between two images. So basically what we do is we calculate the perceptual hash for each picture and compares the hash value to that of the last frame. If they're close enough, we just assume the two frames are similar enough, and we discard this one and assume whatever is detected in the last frame is still there. By doing this, we get similar resource savings. We're transmitting 55% fewer bytes, and we get like about 60% in on all other resources. So discarding similar frames also works. And while a wide variety of applications may benefit from discarding blurry frames and similar frames, there are cases where applications may have its own need for offload shaping. For example, an application may only be interested in human faces, like in motion detector. Then we can probably crop out the human face part and send these small patches instead. We can discard everything else. Another application might only be interested in objects with a particular color. We can also crop that part out and send the small patch instead. We choose color filter as an example, as we are working with Coke cans as examples. We built a red color filter. It basically crops out the red part and sends the small rectangular region only. So by doing this, we also see similar resource savings. We're saving 70% on almost all metrics, and the accuracy loss is only 4%. So now we've seen 3 examples that offload shaping actually helps us save resources while sacrificing a little bit of accuracy. If I'm an application developer and I really want to use offload shaping, what exactly would I want? First, I want a way to specify an offload shaping method specific to my application, because my application may have special needs. And when network conditions change, my optimum shaping strategy may change too. So I may also need a way to dynamically adjust my shaping method to network conditions. Also, in the examples we just talked about, only one shaping method is involved at a time. But there are times I may need multiple shaping methods to work together. For example, if my application is to recognize people's identities, if there's a face in the picture, I can of course crop the face out and do face recognition on it. But if there's not a face in the picture, but someone is wearing a name tag with a QR code on it, I can also crop out the QR code part and scan the QR code to get the person's name. To successfully scan the QR code, I may need a blur detector as well to make sure that the QR code is not too blurry. So I may need a way to specify that I need these 3 shaping methods to work together, and I need to connect them to the way I want. So to address the application's needs like these, we propose an offload shaping API. We designed this API on top of the GStreamer framework. GStreamer is an open source multimedia framework. It can be used to specify complicated graphs in video processing. We repurpose it for offload shaping. This is what our example will look like in this framework. We see a face detector here, a blur filter here, and object detector for QR code there. So the way to specify this diagram in the API, we only need a declarative comment like this. It's okay if you cannot read it, but as long as you can see, it's only 3 lines, and it's actually quite straightforward. So to conclude, in this work, we've shown examples that offload shaping can save resource in terms of bandwidth, energy efficiency, and server workload with only little loss of accuracy. Also, we propose an API for applications to dynamically specify context-specific shaping. And that's the end of my talk. It's a joint work with my colleague Brenda Amos, Zhuo Chen, Kyung Ha, Wolfgang Richter, Babu Pillai from Intel, Benjamin Gilbert, Jan Hakes, and my advisor Satya. Thank you.